Okay, so it's my pleasure to welcome Raul Bindlish. He is the online optimization and nonlinear control leader in Dow Chemical Company. He particularly works with polymer process control, and he's had a number of very interesting projects he's worked on, including nonlinear model predictive control to better control the polymer quality. He's also compared that with linear model predictive controllers, and he's going to be talking about that today during his presentation. So just a brief overview on his biography. He is in the Engineering Solutions Technology Center at the Dow Chemical Company, and they are leading technology development and implementation of model predictive controllers and online optimizers. He has 18 years of experience in this area, and has created significant value for Dow. He has his PhD in chemical engineering from the University of Wisconsin-Madison for his research on nonlinear model predictive control of polymerization processes. And of course, we know about the long history of development there with polymers with Harman Ray and Jim Rawlings, and just a long history of advances in polymers technology there. He's also served as the chairperson on the Asset Advanced Control Optimization Users Group Board and is certified Six Sigma Black Belt. Okay, so that's an overview of Raul, and I'll go ahead and just turn it over.
Thank you for the kind introduction, John, and also for the opportunity to present to this group today. I'm going to be talking about nonlinear model predictive control of an industrial polymerization process. And the way I want to present today, as I'm presenting, I know John mentioned we don't want to hear echoes on the phone, so if you can select your questions, or if you feel like, you can even stop me as far as I'm concerned, as long as the audio is going well. Here's a brief outline of what I'm going to be talking about today. I'll mention a little bit about the literature in this field, talk about the highlights for this problem, and mention what we did for development and application, and then conclude. So the literature that I focused on was specifically industrial nonlinear model predictive control. So there's a good survey paper by Joe Chen and Tom Badgewell that outlines the different applications in industry also. Some people have reported simulation cases and some advances in nonlinear model predictive control for that. There's 3 papers that show results with actual plant data and implementations. All right. So this is a long slide that talks about the different highlights for this nonlinear model predictive control problem. But let me give you a little brief overview on how this came about. So at least at Dow, we have a long history of doing linear model predictive control, and we have attained a lot of success with that. So we use commercial tools to do linear model predictive control, and those controllers have been running continually in closed loop and making a lot of money. But we haven't had an implementation of a commercial nonlinear model predictive control technology in Dow. So this was chosen as the first pilot project to do. So we wanted to demonstrate that there was a need and a value case for nonlinear model predictive control compared to what we have been doing successfully for different plants and businesses. So as we picked a pilot project, we were also careful. I wanted to pick a pilot project where there was significant nonlinearity. So there was a case to use nonlinear model predictive control. I didn't want to do a pilot project and then say, hey, here are the results. We're doing wonderful control and we are making lots of money. I wanted to clearly see the case for nonlinear model predictive control before implementing it. Basically, I wanted to answer the question, the problem does need a nonlinear model predictive controller, not a linear model predictive controller. So this talks about some of the highlights for the problem that essentially mention the nonlinearity in this process. So in this case, we're doing nonlinear model predictive control for a polymerization control problem. And we are actually using the lab quality measures in the feedback control loop. So it's not a advisor whereby we come up with the reactor temperature profile and then we maintain that temperature profile in the controller. So it's not doing that. And within that control problem, it has significant nonlinearities and challenges and interesting aspects. So there are long sampling times for the polymer quality attributes. Some of them are sampled only once a day. The others are sampled twice a day. We got varying dead times depending on the process conditions and rates. The dead times could vary anywhere from 2 to 7 days. The gains are varying a lot from 1 to 20 depending on reactor temperatures and feed rates. And then the process models need to extend for extremely low feed rates. When we first started building this controller, we were told they would run typically about 70% of the nominal rates, and lower than that, they wouldn't want this controller to run. And so it's been a learning and a journey in progress as we have gone through some of these objectives. Over the last 2 years, this controller was first implemented in October 2012, and since then we have learned a lot. So what we learned after the controller ran for like 8 or 9 months, we learned there was a need to run this controller at lower feed rates, which was approximately 35% of normal rates, because of the business conditions. And because of the initial success of the controller, they would rather have this controller run at those really low rates instead of having to go back to the previous way of running things. When we first commissioned the controller, the initial controller was built for the 7 reactors in series. And what we were told back then is sometimes the reactor is taken out of service for maintenance, and that's a short period of time, so there's no need to run the controller in that period of time. But since then, when the business conditions were not very well, were not good, we also had a need to run the controller for a long period of time when they ran the process with only 6 reactors instead of 7. So in short, especially the last 2 bullet items, they signify some of the things that happen in real life. In an industrial case, we build a controller, we do things, and then, in my career here, and what I've realized is whenever we implement anything, things always change because we cannot predict the future. But the nice thing with this technology is it allows us to still realize value. So I talked about significant nonlinearities. So when I'm talking about significant nonlinearities, there are significant nonlinearities in dead time, gains, settling time. So it cannot be controlled using a linear MPC. We verified that. We did a technology assessment and realized that this problem needed a nonlinear controller. So this graphic just shows the extent of nonlinearities a little bit. So on the y-axis, you got scaled viscosity, which is a polymer quality attribute. It's scaled, so you don't get to see the real numbers. Then the horizontal line are the spec limits. So what I'm showing here, the blue line, is the variation in viscosity if the feed rate was to increase 10% from where it is. So it has a dead time of about 200 hours or so, and then it dips down. And it would cross, if you didn't do anything, it would basically go below the lower spec limit. So it shows how the dead time is changing depending on the feed rates for a 10% feed rate change. And the gains are changing too. It's just a simple graphic that kind of tries to highlight the problem. So the one thing to notice here is the dead time and the settling time, right? So the dead time is like 200 hours, it could be 100 hours, so you don't see anything happening in the process. So the models have to be accurate. They need to capture what is happening. They need to capture the nonlinearities, otherwise you're going to have significant spec issues. little graphic on the process itself. 7 reactors in series. Each of the reactor can be heated up or cooled down by using steam or cooling water. We got catalyst coming in, we got monomer and comonomer being fed in, and that's what's going on, and we got the product coming out of the 7th one. All right. When we are in grad school, I mean, a lot of you are in academia. Myself was in grad school at University of Wisconsin, and I did my thesis in this area. Then you have all the flexibility. You can basically build your controller or write your equations and do it in whatever format. You can write Fortran code, MATLAB code, and such, and make a theoretical advance. But there are different challenges in an industrial setting. We have to use a commercially sustainable solution. So it should have the appropriate interface, and the solution should be able to migrate to new operating systems and such. So in this case, we are using APMonitor.com nonlinear controller based on the bounded derivative neural network models. And there's a couple of papers in the literature, Turner and Guyver and Naidu et al., that outline the mathematics behind it. So for this process, we did have a kinetic model. We had a kinetic model in Fortran that had been used by the business for a long period of time because they are using that kinetic model for process development and validation. So what we did is we used that kinetic model and we did lots of simulation cases to construct our BDN models. So in this case, we ended up choosing 50,000 cases to cover the operating region of interest. And essentially, we have a state space kind of formulation where x's are the states and u's are the manipulated variables. These are the measured disturbances, and y is the output that we're trying to control. Like in any model predictive controller, there's 3 aspects here. I want to mention how it is done in this nonlinear model predictive controller. The first is state estimation. We're using an output disturbance model with state estimates using an extended Kalman filter with covariance updates. That's what we're doing. And there's a paper that mentions that, Lee and Ricker, 94 paper, talks about that in detail. For the steady state target calculation, we have a nonlinear objective function to calculate the steady state targets for the outputs, inputs, and the states. And in this objective function, essentially we are minimizing the deviation of the steady state prediction from the desired value and balancing that against how much we would be moving the inputs or the manipulated variables from their current values. That's the desired values. We don't want to move the reactor temperatures unnecessarily. So that's the tuning we do. In addition to that, we have the model equations. We're making sure they get satisfied for the states as they propagate. At steady state, it'll be 0. The derivative will be 0. And we also make sure we have the model equations for the output variables, the measurements. While we satisfy the constraints on the inputs or the manipulated variables and the outputs too. The third part of an MPC controller would be the dynamic regulation, and in this case also we're solving a open loop nonlinear objective function to calculate the move plan, and we are basically minimizing the deviation of the output measurements from the steady state target over a period of time over the horizon, and we're also penalizing the rate of change of movement of how much we're moving the inputs from the current values. And while we do that, we are satisfying the model equations, the states of the model, the output disturbance states, and also the output measurements. We're propagating those equations and making sure they get satisfied. And we have the constraints on the inputs or the manipulated variables, outputs, and the rate of change of inputs too. Okay. So a natural question that should arise in anybody's mind would be, if the process is so nonlinear, before you implemented nonlinear MPC, what was going on at the plant? There was no linear controller, so what was going on, right? So in some ways, some would even classify it as a nonlinear controller was already running. So let me talk about what was going on at the plant. So what we had at the plant back then, we had the model, and it was being run in a simulation mode, and it was providing the reactor temperature profile. So that model was running, and it would come up with a reactor temperature profile that needs to be implemented at the plant. So the reactor temperature profile then would be implemented in the plant using the DCS controller that allows us to do that. So we are basically maintaining the reactor temperatures and the reactor levels using by manipulating the recycle temperatures and reactor feeds. So that was in the feedback control loop, manipulating the temperatures and feeds, the recycle temperatures, reactor feeds to maintain the reactor temperatures. And we were keeping the levels sort of constant. So that's what was going on. The process was getting disturbances with feed rates and composition and ambient temperature. And every time a lab measure came in for polymer viscosity on unreacted monomer content, then basically an adjustment was made to the temperature profile manually, if needed. But there was no direct feedback control loop. It was just open loop simulation that was sending that guidance to the controller. Little graphic on what's going on in an NPC scheme of things. We are essentially trying to minimize the expected deviation of the outputs from the control objectives over a future horizon. And in this case, the horizon is longer than the settling time, so we are making sure we are covering the entire span, and we are minimizing how much we're moving the control inputs or the manipulated variables. And every time we're calculating this move, we implement the first move, and then in the next controller execution time, we recalculated the move plan, and then implement the first move again. So let's talk a little bit about the controller objectives here. So this table shows the relative ranking or priority for the different controller objectives. So things like physical limits, the valve limits for recycle streams, we need to make sure they're honored so we don't try to do something that's not physically attainable. That's going to have the highest priority. The polymer spec limits, they're very important. The polymer viscosity target in this case is the next important limit. Then we also have limits for reactor temperature differences. What those limits are doing is essentially we don't want to heat up in the first reactor and then cool in the second reactor and then heat up again in the third reactor. We want to avoid having that kind of zigzag profile if we can. So we have something called reactor temperature difference CVs that allow us to achieve that. We ended up adding another controller objective recently. It's been about a year or so, and that's to minimize the byproduct content. And this was something we didn't have in the initial controller design. We didn't even have a lab measure for it. But based on the success of this controller, we ended up adding a lab measure for it and also added it as a controlled variable. It gives us better economics when we are able to minimize byproduct content. So the nonlinear control design in this case, we have a cascade nonlinear control design. So the very first question that would arise in a lot of you all's mind would be, why a cascade nonlinear controller? Why not put it all together? Couple of reasons. One of the main reasons is the computational need reason. If you put everything together in one controller, it's going to be very hard to realize it computationally in real time to achieve the objectives that we want to achieve. So we needed to break it for that reason. So let me talk a little bit about that, okay? And also the linearities and nonlinearities where they belong. So I'll mention all that. So the reactor temperatures themselves, with the disturbances coming to the plant, they have a settling time with respect to recycle temperatures and reactor feed that may be anywhere from 3 to 6 hours, depending on rates and process conditions. We need faster disturbance rejection and the ability to maintain reactor temperatures. So that controller is running every minute. The models for that controller or the secondary MPC are more or less close to linear. And that's the reason in the past we were able to achieve those objectives even using a DCS, even in the DCS, even without using a linear model predictive controller. But with a linear model predictive controller, we are doing better than what we were doing with the DCS-based scheme. Now, in the secondary loop or the primary loop, whereby in the past we just had a simulation model that was running and coming up with a reactor temperature profile, those models are the ones that are significantly nonlinear. So that's the primary MPC. The goal of that primary MPC controller, which is extremely nonlinear, is to control the polymer quality attributes in a closed loop. So the attributes that we are looking at are polymer viscosity, unreacted monomer content, and byproduct content. These quality attributes have a settling time of anywhere from 10 to 15 days, so depending on rates and conditions, and we are measuring them only either once a day or twice a day. So given that we don't really need as fast a disturbance rejection, and we are able to get by running that controller only once every 30 minutes. As mentioned before, initially the byproduct content was not in the original scope of the controller. We ended up adding it after we had initial success with the controller, and we got a lab measure for it. Both controllers have do model effects of the measured disturbances that enter the plant, which may be in the form of feed rate disturbances, composition disturbances, and ambient temperature. All right. This graphic or this gives an idea of how much, so what's the problem here, right? If nonlinearity is nonlinearity, but if the process doesn't change, then the nonlinearity is not as big a problem, right? So the reason, so if you look at this graphic, what I'm showing here is this is the normalized feed rate to this process is about 60% here, and then it suddenly drops to about 30%, then they end up raising the rates back up to 60% and stay there, then it suddenly drops again and they raise it back again and they end up being raised again. So what's happening here is the place where this plant is situated in our site, it gets impacted by upstream plants and also gets impacted by downstream plants. So it's in the middle, sort of. So because of that, and so it gets impacted by disturbances everywhere, so it has to undergo a lot of rate changes. So in this case, those rate changes are significant and severe, especially if there's a plant trip and such. So in this case, this is a significant speed rate disturbance, and that is going to impact the polymer quality coming out of this process. So if you look at the x-axis, then you're going to be saying, okay, this is about 4 months of data, but you got to realize these disturbances are happening over 20 days or so, but the settling time of this process for the polymer quality attributes can be anywhere from 10 to 14 days. So these are like sort of fast-moving disturbances for that settling time. So the initial project, when it was chartered, the goal was to show better improvement in control, especially for polymer viscosity. That's how the project was chartered. So this shows baseline data, collected annual data from last year, the year prior to doing this project. This shows how the viscosity was doing. This is the upper spec limit. This is the lower spec limit. It shows how it was wandering off from the spec limit and also had a wider spread. After the controller has been implemented, we have had, in this case, this is like 4 months of data, but we have even collected more data in the last 2-3 years. There have been much lesser excursions, maybe only very few, handful. And we also have a much lesser standard deviation, if you may say, for polymer viscosity. So we have tighter control and lesser excursions from the spec limit. So that baseline was collected for the case when the nonlinear model was running continually and was suggesting the profile to the plant, and the profile was the only thing, the reactor temperature profile was the only thing that was in closed loop, not the quality attributes. But the nonlinear model itself was running continually, and that profile was fine-tuned manually. So the second objective, or the important polymer quality attribute, is the unreacted monomer content. The unreacted monomer content, the graph on the left side shows the baseline data. In this case, there's bigger spread, and really, more importantly, there's more excursions with unreacted monomer content, and that causes all kinds of problems and plant trips for some of the downstream plants. So we had some of those events, but after we implemented this controller, we've been able to run this controller and the process without excursions on unreacted monomer content. So we've been able to keep it within specs. So the other thing to note is, after the controller ran for about a year or so, then we ended up deciding that we would like to add another control variable, which is the byproduct content. It's an economic measure of the process, so we didn't even have a lab measure for it. We just had a simulated result for it. So the old controller couldn't do anything, the old simulation model just had a simulation of that, but we didn't have a lab measure for it. So we were sort of trying to minimize it, but running it without any lab measure. But in the new controller, we added the lab measure for it, added the models for it, and we've been able to minimize the byproduct content when we can. So this graphic shows is the spec of that byproduct content, which is like 0.27 or so. So we've been able to keep it much lower than that, but when needed, we have to let it rise as needed. So in this case, it actually has an excursion all the way to 0.26, but it still stays below the spec limit when needed. The results: we have better control of polymer quality measures. We've been able to do that, especially for polymer viscosity, unreacted monomer content, and we have also added another controller objective that allows us to minimize byproduct content. Now, talking about reduction in variation in polymer viscosity, because that was the original charter of the project, we've been able to reduce the standard deviation in polymer viscosity by 34%. And we first chartered the project thinking that we should be able to do about 20–25%. So we've been able to do slightly better than that. This controller has been in continuous use since October 2012 to maintain polymer quality at specified production rate requirements. So the production rate requirements are changing depending on what's happening in an upstream plant. So we undergo a lot of feed rate disturbances and such, and we have to maintain polymer quality while those rate changes happen. The Cascade Nonlinear Model Predictive Controller structure is successful in an industrial setting. It allows us to achieve the process objectives that may have different settling times and may even have linear versus nonlinear models. It also allows us to address the computational needs of the associated dynamic optimization problem so that we can run the controller in real time. I'll mention one more thing. After the initial success of this project, what has also happened is we have now 2 or 3 more active projects that we've been working on based on the initial success of this project. So it's been a long journey. Apart from the technical learnings on the technology and process that I shared with you today, I also want to mention as we do these things, one of the things, especially in an industrial setting, as we increase or enlarge the scope of the controller to make it successful to address the plant problems, is to have the partnership with the plant people and learn from them as we implement these solutions. That's all I have to say today. At this point, I'll be more than willing to answer any questions or comments that you may have.
Okay, fantastic. Thank you, Raul. That was an excellent presentation. We'll go ahead and open it up to questions now. If you'd like to either unmute your microphone, you can ask a question, or you can put a question into the chat window. And so just to start, we have one question from Mike Tay. He asks, was the fundamental model steady state or dynamic? And then if steady state, how were the dynamic models in the NMPC developed?
Okay, well, this fundamental model, we had both the steady state representation of the fundamental model, but it essentially was a dynamic model, and we have the dynamic model. We had the fundamental dynamic model, and we use that to establish the dynamics. But in addition to that, I want to mention we used the model to come up with our initial models. But we fine-tuned our models because plant does not, our models are an approximation of the reality. So even though we had a dynamic model, we had to fine-tune some of the observed dynamics slightly for some of the control variables based on what we saw in the plant.
Okay, fantastic. We have another question here, bounded derivative networks, the models that are used supposedly in that outer loop. Have you had to go to any new grades, new products that you're manufacturing, and how do the models extrapolate? What's the process of maintaining those models?
Excellent question. So I think that's really one of the most interesting challenges as we have learned the process and also gone through those learnings. So one of the things that happened is when we went to lower rates, we had to develop new models, and we saw learnings. So the models extrapolate reasonably well, but there's some tools in the software itself. So we have to ensure monotonicity to make sure they extrapolate well and they are relevant. So we have to examine the models, and we had to do a lot of model work to make sure the models were not over-parameterized and did not have higher orders unnecessarily, and that would result in poor extrapolation. So we had to examine the models and the first derivatives very closely.
Okay, great. So we have another question. And maybe you could go back to the slide where you show the primary and the secondary NPC controllers. But the question is, why does the process need to have a secondary NPC controller?
Good question. So in the past, we were controlling the reactor temperatures and levels using a DCS control. But by having an MPC controller for that, we are able to control the reactor temperatures and levels a little better than a DCS strategy, and we are able to use recycle temperatures and all the intermediate reactor feeds to maintain all the reactor temperatures and levels simultaneously, and basically it's a better setting, that's all. We are able to take advantage of the multivariable interactions instead of single input, single output pairing in a DCS.
Great. Okay, we just have another question here that just came in. What processes are included in the model other than kinetics and heat transfer? Are the kinetic parameters estimated?
So in this case, we had the nice thing, the business and the technology people had already been using this model to develop their process and had validated this model. So they had the validated kinetic parameters. We didn't have to do estimation of those kinetic parameters. So they had validated this model with plant data. So we had a validated model, so we didn't have a need to do that.
Okay, great. And then I guess the other part of the question is, what processes were included in the model? So was it mostly the reactors, or did you have some of the finishing area? What was the scope of the model?
The scope of the model essentially was the reactor area, not the finishing area. The finishing area we approximated by simpler things. So the scope of the kinetic model is the 7 reactors in series, and that's really the big part of the model anyway.
Okay, great. Okay, let me scroll down here. Okay, where are the NMPC models in the Cascade framework implemented? Software? How are they solved via solvers? So just a question about where are the NMPC models in the Cascade framework implemented, and then how are they solved with the solvers?
Okay, very good question. So this actually reminds me of my graduate school days somewhat. So when I had the freedom there, I could write code wherever I wanted to write, and I could use some of the NAG routines and some of the state-of-the-art optimization software. In an industrial setting, I don't have that luxury. So the NMPC models are in the primary model predictive controller, and they're implemented in the Aspen Nonlinear Control Framework, which is a BDN. They're implemented as BDN models, and they're implemented on a server, which is at the plant, and we basically have to use the optimization algorithms within that controller. So we have to make it work to come up with the right answer and make sure so we do that and make sure it works in that framework.
Okay, great. Another question, how well is the estimator working in identifying the states from the outputs? Any negative concentration estimates?
No, we didn't see that. We didn't see the negative concentration estimates. So we haven't seen that as being a problem for the problem we are looking at. That's something to watch for, especially with an extended common filter, absolutely.
Was it very hard to tune the filter?
It was hard, but not as hard as I would have thought initially, to be honest. I think if we had the right noise dynamics or the variance initially, we actually were able to do what we needed to do without having trouble there.
Okay, so another question, a question on batch processes versus continuous processes. So the question is, are the processes shown in the slides continuous? What is your idea on application of your method to CSTR or batch processes?
Okay. The processes shown in these slides are continuous. So going to the CSTR, yes, the controller and the math here applies directly. In a batch process, the objective is different. The objective is now to minimize batch time. And we're not going to get as much continual disturbances. So we don't have these disturbances that are hitting us. but we have lesser disturbances that hit us, and we are able to control the batch better, but we have to minimize the batch time. So it's a different controller objective, and we are looking at, and that's something, that would be a different controller objective. It won't be this controller formulation.
Great. Okay, so we have two questions that are very related. I'm going to go ahead and ask the first question first, and then we'll get to the second one. Is the process model used in the primary NMPC retuned in another loop, offline manually, or is it rarely retuned?
So what has happened is we have been asked to, so we have added or examined the models or extended the models to different operating conditions. So in this case, after running the controller for a year or so, we ended up developing models for lower feed rates, 35% versus 60 to 70%. We also came up with models that would work with 6 reactors instead of 7 reactors. So that's one thing that happened. So as far as retuning is concerned, I think there was a lot of retuning of the models when the initial deployment happened. So there was a lot of that. But once we did due diligence and we did our hard work there, it was lesser of a requirement. What happened after that was more of the requirements had changed. They wanted to run at lower rates. They wanted to run at 6 reactors on 7 reactors. So I think the requirements are always going to change in an industrial setting. And when you first deploy the controller, even if you have done everything you have done, there will be a lot of examination and tuning for an extended period of time to make sure everything works properly. And in this case, we want to do that because what happens now is based on what happened 7 or 10 days earlier. So the nice or bad thing is, if something is good now, you don't see the effect of it until 7 or 10 days, and then it's too late. So you just want to make sure you have what you need, and you have to answer those queries and collaborate with the plant and technical people appropriately.
Okay, great. So the follow-up question, the second one, can you just give us some insight as the process is changing, how is the nonlinear model updated? Do you have to start from scratch, or can you start from the prior one and then update incrementally?
So in some cases, in most cases, we can start from our existing knowledge. But I think the bigger thing to me is it's not a turnkey project the way we do things here. So we have at least I have made sure I have the appropriate engagement with the appropriate people at the plant and tech center level. So even when we first deployed the controller, we even had a weekly placeholder meeting for like months or about a year or so. So it allows me to watch this controller. This was the first one that we had done at Dow, and we wanted to make sure it was a success. Otherwise, it would have been turned off and said, okay, this was doing crazy things. These guys came and tried to do something. Let's turn it off and end of story. But because we engaged them and learned from them and also made sure they understood what the controller was doing or why it needed to be retuned, then only they would allow it to run, especially on Friday night and Saturday night when they are in the control room and they are managing the emergency, not anybody else. So that's the insight. I think in my mind, the tuning can happen as a small tuning, but there's a lot of process knowledge that needs to be assimilated. We never had to rebuild the controller from scratch. But it was more a question of understanding what the needs are and basically doing the right thing for the process.
Great. Could you go to the slide where you showed the before and after with the product quality limits?
With the what?
The distribution that showed the. Okay, so question related to this is there a limit or band for the control outputs before the NMPC performs a control action?
So let me make sure I understand the question. So the limit for what now?
So just the question is, does the controller only ask when it predicts it's going to be going outside of this deadband, or is it always trying to drive to a center line value for these?
Okay, good question. I guess this doesn't really show it very clearly. So the polymer viscosity, we are controlling it to a target. So that's the only polymer quality attribute we're controlling to a target. The unreacted monomer content, we are not controlling it to a target. We're just trying to make sure it does not have an excursion. And the byproduct content, we are always trying to minimize it. So this one, the first one, the polymer viscosity, we're controlling to a target. I didn't show it here, and it's really in the middle here. We're controlling it to a target, but we also have the spec limits that are very important. So there is a value in controlling it to a target. So we are controlling it to a target.
Great. Okay, so we have a question. And this individual had a question about your first principles models. You said that you at Dow had these validated models, and then the question is, what would be an advantage of using a first principles model versus a state space model or these empirical models, and any challenges that would arise in splitting the controller into two with a first principles and possibly linear model or empirical model?
Okay, I'll try to answer. Okay, I think I understand what this individual is getting at. So in my mind, there's some things here. So we have the first principles model, and for some of the finishing and mixing kind of areas, we may have some empirical representations, and those are adequate and have the appropriate physical insight. And we use that, and that's what we call our fundamental model. So it's the first principles with kinetics, and also some empirical representation that captures the mixing and the finishing area. So that's what we have. Now the question is the advantage or challenges of doing that compared to using a BDN model. We needed to use a BDN framework because we wanted a commercial control solution in the plant that's sustainable. So the challenge here was to ensure that the BDN extrapolated well without creating instabilities. So that was a challenge. We examined the model predictions, the first derivatives of the manipulated variables against the polymer quality attributes, and examined them for monotonicity and made sure they made sense. So we had to do that. Otherwise, we would have problems. And with the first principles model, we wouldn't have to do that, but we didn't have the luxury of using the first principles model directly.
Great. Okay, well, I think we're about out of time now. We have more questions than we have time to answer today. So if you'd like to ask any additional questions that weren't answered today during this discussion, feel free to send those to me and I'll forward those on to our speaker. But Raul, excellent job with the presentation, and it certainly gives some valuable insight into the work that you've done in terms of NMPC model. So very exciting work, and thank you for your presentation.
Thank you, John, and thanks to the audience too, and for the interaction today, and I welcome this opportunity.
Okay, great.